system, you know. There are real numbers. They split as irrational and rational. And then within the rationals, you have things like integers, and then like whole numbers, and natural numbers, right? That's what you know. So then there became a need for a little bit more than this. So a lot of times in math, we get to something we can't calculate, it's undefined, or there's no solution, and that's okay. It just doesn't work for that context. But there was an issue, and if you look up where this is used today, it comes up mostly in electrical engineering type of fields, where we need to take square roots of negative numbers, finish calculations with them, and at the end, they turn back into real numbers when we're done with our calculation, but there had to be something that could get us through the calculations. So we needed to add something onto this number system that wasn't real, okay, something that didn't fit in there, like when we were taking the square roots of negatives. Okay? And so they called these imaginary numbers. I know, nice name, right? I'm sure you guys are like, why do we need to know it if it's imaginary? And so, I'm going to change this label in here a little bit. Yes, Marcus?
So like variables where it's numbers that are used to place.
So, well, the imaginary numbers are specifically square roots of negative values. Okay? So specifically having a negative underneath the square root. Then we now call this the complex number system, meaning a complex number could have a real part and an imaginary part with it. Okay? So we're going to look at a number system that a mathematician discovered and made up and all this today. And you're like, well, I could make up my own number system, and you could. But it wouldn't stick around and nobody would use it unless it actually had value. So his has value because it connects to the real number system and is used in those things like electrical engineering and stuff like that. Okay? And the reason we talk about it here is because it relates to that idea that quadratics have no solutions or no real solutions, but there is a way we can write those numbers in a different way when that negative shows up underneath the radical. So when a negative shows up underneath the radical, they called it the imaginary number system, and so the unit is just I. So now when we see a negative underneath the radical, if the problem doesn't say we're only allowed to work with real numbers, then we're going to include I as part of what we are telling people is happening there, okay? How you would write it in simplest form is I. Don't leave square root of -1. We would call it I if you're using it, okay? What this means is kind of this unique idea. They didn't really define it this way. They really defined it this way, that I squared would be -1. Meaning if you took a number and times it by yourself, you got a negative, which never happened before. That's why it had to be outside the real number system. Okay? So it's not like we're changing the rules of what you knew. This was a different addition to the number system. It doesn't change the rules of what you know. It says, hey, we have a need for this other thing. We have a need to take something and square it and get a negative, which doesn't happen in the real numbers. So I'm going to call I the number that you can square and get a negative. Okay? Which means this was defined, which means I is what we're going to call it if we see the square root over the negative, okay, without the squared part. So think about what this means for different powers of I cubed could be thought of like I squared times I, but I squared is really what? What was it defined as? -1. So this is really -1 times I, which we would call negative I. And then I to the 4th would be like I squared times I squared. But what is I squared? -1. So what is -1 times -1? +1. Okay, so this is why his number system stuck around, and yours might not if you made your own, has this deep connection to what we're doing, and again, there was a need for it, okay? If you did I to the 5th, I to the 5th would be like I to the 4th times I. But what's I to the 4th? 1. And so I to the 5th is really just the same thing as I. Right? Okay. New number system. So I to the 6th. If we thought of I to the 6th, we could think of it as I to the 4th times I squared. But I to the 4th is really just 1. And then we're left with I squared, but we defined I squared to be -1. So what do you see happening here as we keep going through different powers of I? Okay, so if they can go back to real numbers, they're either 1 or -1. Marcus?
Then you're in a pattern, I, -1, -I, and then 1.
Good, and then like the 5th power was just like having the 1st power again and the 6th power, Jonathan?
Something that is being if I can think of it as I fifth power times I. Big minus I.
Times I. Times I, because you would add the exponent. So when we look at a high power of I, like I to the 231st power, I don't really want to write out all the powers. But when I was doing I to the 5th, notice every time I came up with an I to the 4th, I to the 4th was just equal to 1. So really I would want to think of I to the 231st is really a bunch of I to the 4ths, right? As many as I can get out of there, because 1 times 1 times 1 times 1 times 1 isn't going to change anything. And then like what's left after all those I to the 4ths? So really I'm going to take 231 and divide it by 4, okay, because I want to know how many powers of 4 to use. And I would get that 4 goes into 231 57 times with 3 left over, right? That means I would want to use I to the 4th 57 times, but I would have left over how many powers of I? To the 3rd. And what does I to the 4th become? 1. So what is 1 to the 57th power? 1. So I to the 231st power is really the same as I to the 3rd power, and then you need to know this stuff right here. So I to the 3rd power, the simplest way to say that is the negative I. So really you should never have anything written with a higher power than 1 on I, because it either turns back into a real number, right? Or it's some version of I to the 1st power, either positive or negative. Okay, so if you have a power on I, you haven't simplified it all the way. Okay? So I to the 120th power is like I to the 4th 30 times with nothing left over, because 4 times 30 is exactly 120. So what is I to the 120th power? Right. Good. Okay, so are we okay with how this kind of new idea works? Yeah.
If it's divisible by 4, is it going to be always a positive number?
Mm-hmm.
And if it's not divisible by 4, it'll be
But then if it could still be even and be a negative number if it's like divisible by 2 but not by 4. Okay. All right, so you're going to watch most of this at home. But the idea is now when you see square root of -24, unless it says only deal with real solutions, you're not done. You can now write this as a complex number. Because we would think of the square root of -24 as the square root of 1 times the square root of 24. You're going to simplify the square root of 24 as you normally would. Break it down, find the perfect squares, all this kind of stuff, and you're going to get 2 rad 6. But what do we now call the square root of -1? I. So this number you would most likely see written, the order doesn't really matter, but it's just kind of etiquette or whatever the way that they write it. You would see it as 2I rad 6. And what that would tell you is this isn't a real number. This is an imaginary number because it had a negative underneath the radical. Okay? And so the way that we would use that in the context of what we're doing is every time we do the quadratic formula or we complete the square, you know how earlier in our note guide we got stuck at one problem with the negative underneath? We now wouldn't get stuck. So for example, I'm just going to do part A and then it's going to show you in the video how to add and subtract all this stuff. If we moved the 12 over to the other side and then divide by 3, we would have this and we would have said, oh, no solution, I'm stuck. Well, you're right, there's no real solution and it will have no x-intercepts, but it does still have some complex solutions. How would I write the solutions to this? Jonathan? Good. Okay, so rad 4 is 2, so you're thinking it through. So rad 4 is 2, and this is an I, and then we forgot one thing. Natalie? Plus or minus, because we square rooted both sides. So all those same rules apply. Okay. So the way it's going to work, as you look in the video that you're going to see, you can add, subtract, multiply these. You can rationalize the denominators. And what you're going to see is that it's kind of like using like terms, how x's get added with x's and y's get added with y's. Real parts can be added together. Imaginary parts can be added together. So you can add together two different numbers. You're going to multiply like normal, but you're going to have this extra step. Anytime that I squared shows up, that converts that imaginary back into a real number. You need to use that as -1 and then finish simplifying where you can. Okay? So the video is about 10 minutes. It's just going to take you through adding, subtracting, and multiplying, and then how to change it so that you don't have I in the denominator. So just like you wouldn't put a radical in the denominator, I is not a rational number either. I is an imaginary number. It's part of the complex. So we wouldn't normally keep that in the denominator either. So it will show you things that we can get those out. And that's it. It's going to show you those two things. So basically just how to do the operations. Okay?